Hello there, random smart person on the internet. I have a special video today. In every video, I always end it with the phrase, comments are good for the YouTube algorithm. Psst, hey, come here. Comments are good for the YouTube algorithm. 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 Because it is true, comments are good for the YouTube algorithm. Your comments inspire me to make certain videos. And this video is brought to you by one of those comments that was left because it was good for the YouTube algorithm. One of my subscribers asked, why or how space expands? Now this is an excellent question, and it excites me so much that I turned this comment into a video. So I got to working writing my script for the video. I was thinking of all kind of science facts to put in the video, and the more I typed, the longer the script became. I kept typing and typing, and eventually my script became 22 pages long. I was typing so long that dust began to cover my collections in my room. Man, I really have to clean my room. Normally my scripts are around 4 to 5 pages, but I knew if I was going to produce this video anytime this year, I would have to cut it down. But then I thought, no, I have a subscriber that wants to know a topic about space, and I want to teach everyone about the cosmos. So it is my job, nay, my duty to provide the best science content on YouTube.
All viewers, subscribers, and aficionados of the Fun with Sim YouTube channel are hereby advised in the interest of preserving the delicate balance of ego and humility that the channel's claim of being the best should be taken with a generous pinch of salt. Whereas the channel in the relentless pursuit of self-aggrandizement may proclaim itself as the paramount purveyor of content of its chosen domain, be it known that the channel, by virtue of the ever-evolving, capricious, and highly subjective nature of the World Wide Web, cannot guarantee that it is, in fact, the zenith of YouTube excellence. It is to be understood that the term best is employed herein as a form of hyperbolic self-promotion and is not intended to be constructed as a legally binding assertion of absolute supremacy. By engaging with the channel, viewers hereby acknowledge that the channel is not immune to the vicissitudes of the internet, the shifting sands of public opinion, or the potential rise of other best channels which may eclipse in popularity, hilarity, or cat video content. In conclusion, while the channel endeavors to provide content that is entertaining, informing, and occasionally mind-boggling impressive, viewers are encouraged to exercise discernment, maintain a sense of humor, and explore the vast universe of YouTube in the search for their own personal definition of the best.
So instead of waiting to the end of the video, click like, subscribe, and comment on any topic you want to learn about space. As you can see, those comments are good for the YouTube algorithm, and I will turn it into a video. Now let's get back to the question that was the inspiration for this video. Why or how space expands? I'm going to answer this into 2 parts. First will be how we know space is expanding, and second is what is causing it to expand. And if you stay to the end of the video, I'll provide you with some bonus information about possible ways the universe could end. And maybe even an extra bonus, but you have to wait till the end. The concept of an expanding universe is rooted in Albert Einstein's theory of general relativity, which he formulated in 1915. General relativity proposed that the fabric of space-time itself could be influenced by the presence of mass and energy. In the early 20th century, Belgian astronomer Georges Lemaitre and American astronomer Edwin Hubble independently provided crucial evidence for the expanding universe. The expansion of the universe is driven by a factor known as the cosmological scale factor. This factor describes the size of the universe as a function of time. When the cosmological scale increases, the universe expands. And when it decreases, the universe contracts. The expansion is attributed to the Big Bang Theory, which posits the universe originated from a hot, dense singularity approximately 13.8 billion years ago. As the universe expanded, it cooled and allowed the formation of galaxies, stars, planets, and all the structures that we observe today. Note that the Big Bang was not an explosion in space, but it was the rapid expansion of space. Nothing exploded, and it didn't happen at one singular point, but rather it was a rapid expansion of space everywhere. How do we know the universe is expanding? Several pieces of observable evidence supports the idea of an expanding universe. The first piece of observational evidence is that most galaxies are redshifted. Redshift is a phenomenon in which spectral lines of light from different objects, such as galaxies, appear to have shifted towards the longer wavelength or redder end of the electromagnetic spectrum. This shift occurs because the source of light is moving away from the observer, and it is a consequence of the Doppler effect. The Doppler effect is commonly experienced when the pitch of a siren or horn from a moving vehicle changes as it approaches and then moves away, but instead of sound, it is with light. The discovery of the galaxy redshifts dates back to the work of American astronomer Vestor Slipher in the early 20th century. In the years leading up to the 1920s, Slipher observed the spectra of many galaxies and noted that a majority of them exhibited a redshift. Slipher's measurement indicated that these galaxies were moving away from Earth. However, the significance of this observation was finally fully realized with the work of Edwin Hubble. In the 1920s, Edwin Hubble made a groundbreaking discovery that revolutionized our understanding of the universe. Hubble combined Slipher's redshift measurements with his own observations of galaxies and developed a comprehensive study of galactic motion. He noticed a pattern. Galaxies far from Earth exhibited greater redshifts, which indicated they were receding at higher speeds. Hubble's observations led to the formation of what is now known as Hubble's law. Hubble's law states that the velocity of recession, the speed at which a galaxy is moving away, is directly proportional to the distance of the galaxy from Earth. Mathematically, it can be expressed like this. Where v is the velocity, h0 is the Hubble constant, a measure of the rate of the universe's expansion, and d is the distance to that galaxy. This relationship provided strong empirical evidence of the expansion of the universe. Hubble's law confirmed that the universe is not static, but is expanding. Galaxies are moving away from each other as indicated by their redshifts when observed from Earth. The linear relationship between the galaxy's distance and velocity supports the Big Bang theory. Hubble's law allows scientists to estimate the Hubble constant, a vital parameter in cosmology. The value of h0 provides information about the age and rate of expansion of the universe. By measuring the Hubble constant and using Hubble's law, astronomers can estimate the age of the universe. This estimate has been refined over the years and currently stands at approximately 13.8 billion years. The redshift of galaxies is a cornerstone for the Big Bang theory, the prevailing model of the universe's expansion and evolution. As the universe expands, galaxies move away from each other, and this motion causes redshift of their light. Remember that a scientific theory is not a guess. It is a well-substantiated explanation of the natural world. It incorporates facts, laws, and hypotheses. Redshift is not just a simple observation. It is a powerful tool for measuring cosmic distances. By studying the redshift of galaxies, astronomers can determine their velocities and consequently their distance from Earth. This information is essential for constructing the cosmic distance ladder, a method used to estimate distances of objects in the universe, from nearby stars to the most distant galaxies. The cosmic redshift formula is a fundamental equation used to describe the observed redshift of light from distant astronomical objects, such as galaxies and quasars, due to the expansion of the universe. This formula is based on the principle that the wavelength of light from distant sources is stretched as the universe expands, resulting in a redshift of spectral lines. The cosmic redshift formula is expressed as this, where z is the redshift, lambda observed is the observed wavelength of light received on Earth, and lambda emitted is the emitted or rest wavelength of the light source. The redshift z is a dimensionless quantity that characterizes the relative change of wavelength of light due to the expansion of space. It is a measurement of how much the universe has expanded since the light was emitted from the source. A positive value of z indicates that the light has been redshifted, while a negative value corresponds to a blue shift, which means that the object is moving towards us rather than away from us. This is relatively rare for distant astronomical objects, since only objects that are moving towards us are in our local group of galaxies, where the Milky Way's gravitational pull can influence other galaxies. In practical applications, the cosmic redshift formula is often used to calculate the redshift of galaxies and other celestial objects observed in the universe. The redshift provides valuable information about the velocity and distance of these objects, contributing to our understanding of the large-scale structure and expansion of the cosmos. It is important to note that the cosmic redshift formula is a simplified expression that works well for low redshifts and is derived from the basic principles of the Doppler effect. For higher redshifts, or when considering the effects of general relativity on the expansion of the universe, more complex cosmological models, such as the Friedmann equations, which I will cover in a bit, are used to accurately describe the relationship between redshift and the expansion of space. The discovery of the redshift of galaxies and its evidence for the expanding universe is a monumental achievement in the field of cosmology. It has provided compelling support for the Big Bang theory and has reshaped our understanding of the cosmos. Redshift not only serves as a fundamental concept in modern astronomy, but has also played a crucial role in determining the universe's age, size, and ultimate fate. The observation of the redshift of light of galaxies continues to be a central focus of the astronomical research and exploration, further enriching our comprehension of the vast and dynamic universe in which we reside. The second piece of observation that supports the idea of an expanding universe is the cosmic microwave background radiation. The cosmic microwave background, CMB, is a crucial piece of evidence in our quest to understand the universe's origin and evolution. It is the faint glow of the microwave radiation that permeates the cosmos, and its discovery has revolutionized our understanding of their universe's history. The CMB is a form of electromagnetic radiation that fills the universe. It is often described as the afterglow of the Big Bang. The CMB consists of microwave photons, which are low-energy, long-wavelength particles of light. The CMB is remarkably uniform and nearly isotropic, meaning that its temperature and intensity are almost the same in all directions of the sky. Its temperature is measured at approximately 2.7 Kelvin. negative 454.8 degrees Fahrenheit, just slightly above absolute zero, making it the most perfect black-body radiation ever observed. The discovery of the CMB is attributed to Arno Penzias and Robert Wilson, two astronomers working for Bell Labs in New Jersey in the early 1960s. They were conducting experiments with a large radio antenna designed for communication purposes, but noticed a persistent background noise that they couldn't eliminate. The noise appeared to be coming from all directions in the sky, regardless of the antenna's orientation. After ruling out terrestrial sources of interference, including scraping bird poop off of the antenna, Penzias and Wilson concluded that they had stumbled upon something truly remarkable: a uniform microwave radiation filling the universe. Their discovery was the first direct evidence of the CMB, and they were awarded the Nobel Prize in Physics in 1978 for their groundbreaking work. The cosmic microwave background is of paramount importance in the field of cosmology for several reasons. The CMB provides compelling evidence in support of the Big Bang Theory. Its uniformity and temperature fluctuations match the theoretical predictions of the universe's early, hot, dense phase. The power of a theory is in its prediction. The Big Bang Theory predicted a nearly uniform CMB nearly a decade before it was discovered. The CMB serves as a baby picture of the universe when it was only about 380,000 years old. It allows us to study the universe's conditions shortly after its birth, long before the galaxies and stars have formed. The CMB's temperature fluctuation contains valuable information about the universe's composition, geometry, and evolution. By analyzing these fluctuations, cosmologists can determine parameters such as the density of matter, dark energy, and the curvature of space. The CMB also supports the theory of cosmic inflation, which suggests the universe underwent a rapid and exponential expansion shortly after the Big Bang. Inflation explains the uniformity of the CMB and the large-scale structure of the universe. The cosmic microwave background is a cosmic relic that has reshaped our understanding of the universe's origin and evolution. Its discovery and study have provided crucial evidence for the Big Bang Theory, offered insight into our early universe's conditions, and allowed cosmologists to refine their understanding of the universe's composition and structure. As technology and our knowledge of cosmology continues to advance, the CMB remains a valuable tool for unraveling the mysteries of the cosmos and expanding our comprehension of our universe's remarkable history. The third piece of evidence that the universe is expanding is the distribution of galaxies and large-scale structure of galaxy clusters across the cosmos. Imagine a vast interconnected network where galaxies are not scattered randomly, but are organized into a cosmic web. This intricate structure resembles a spider's web of the largest scale, and is one of the most remarkable discoveries in the field of astrophysics and cosmology. The cosmic web is a testament of the universe's underlying order and complexity. At the heart of the cosmic web are galaxies. Galaxies are colossal systems of stars, gas, dust, and dark matter bound together by gravity. They come in various shapes and sizes, from spirals like the Milky Way to elliptical and irregular galaxies. Galaxies are not perfectly evenly distributed throughout the universe. Instead, they are grouped into clusters and superclusters. Galaxy clusters are vast conglomerates of galaxies held together by gravity. These clusters can contain from a few hundred to a few thousand galaxies. Superclusters, on the other hand, are even larger structures that consist of multiple galaxy clusters. The cosmic web gets its name because of its web-like appearance. The structure consists of vast, thread-like filaments of galaxies and immense, bubble-like voids between them. These filaments form the backbone of the cosmic web, connecting galaxies and galaxy clusters together. There are three key characteristics of the cosmic web: filaments, voids, and superclusters. Filaments are the long, thread-like structures of galaxies that are often found connecting galaxy clusters. These filaments can be hundreds of millions of light years long and are densely populated with galaxies. The cosmic web contains vast voids, regions of seemingly empty space with very few galaxies. These voids can be equally expansive, stretching for hundreds of millions of light years. Superclusters are the largest coherent structures in the universe, composed of numerous galaxy clusters and stretching over immense distances. They serve as junction points connecting filaments and voids. The formation of the cosmic web is a complex process governed by the gravitational interactions between the matter in the universe. Shortly after the Big Bang, tiny fluctuations in the density of matter led to the formation of regions of higher and lower density. Over billions of years, gravity caused denser regions to attract more matter, eventually forming galaxy and clusters connected by filaments. The study of the cosmic web provides profound insight into the universe's history. It helps scientists understand the distribution of matter in the cosmos, the role of dark matter in galaxy clustering, and the expansion of the universe. The cosmic web also serves as a framework for understanding how galaxy and galaxy clusters are distributed, providing crucial clues about the large-scale structure of the universe. The cosmic web is a breathtaking testament to the universe's grandeur and complexity. Its intricate structure of galaxy and galaxy clusters, organized into filaments and voids, offers a glimpse into the underlying order of the cosmos. Understanding the cosmic web is not only a fascinating journey through the universe's architecture, but also a crucial endeavor for unraveling the mysteries of our vast cosmos and our place within it. Now, we know the universe is expanding without a doubt, but what is causing it? Before I answer this, we need to know what makes up the universe. First is ordinary matter, also known as baryonic matter. This is the stuff of which planets, stars, galaxies, and all known matter in the universe is made of. It consists of particles called baryons, primarily protons and neutrons, which form atoms when combined with electrons. Ordinary matter interacts through electromagnetic forces, giving rise to familiar chemistry and physics that we observe on Earth. Ordinary matter consists of a mere fraction of the total mass energy content of the universe, estimated at approximately 4.9%. Wait, if what we call ordinary matter only constitutes 4.9% of everything in the universe, is it really ordinary, or should we call it rare matter? This includes all matter that we detect with instruments and telescopes. Ordinary matter is well understood and extensively studied. It is the realm of particle physics and astrophysics. We know it exists because we can directly observe, measure, and interact with it through experiments and observations. Its presence is evident in stars, galaxies, and cosmic structures, as well as through its electromagnetic interactions, such as the emission of light. The second is dark matter, a mysterious and invisible form of matter that does not emit, absorb, or interact with the electromagnetic radiation like ordinary matter. It does not consist of atoms, but instead comprises of exotic particles yet to be discovered. Dark matter's gravitational influence is what holds galaxies together and forms the invisible scaffolding of the cosmos. Dark matter makes up about 26.8% of the universe's total mass energy content. Dark matter's existence is inferred from its gravitational effects on visible matter, such as galaxies' rotations and the behavior of galaxy clusters. It has not been directly detected, and its nature remains one of the most significant unsolved mysteries in astrophysics and particle physics. Even though it has not been directly observed, we can observe its effects, such as gravitational lensing and keeping the structures of galaxies together as they rotate. Research efforts include experiments in deep underground laboratories and the search for candidate dark matter particles, such as WIMPs, which stands for Weakly Interacting Massive Particles. Finally, and most importantly for this video, is dark energy. Dark energy is one of the most mysterious components of the universe. It is a form of energy that is responsible for the accelerated expansion of the universe. Dark energy is a form of energy that fills the vast expanse of the universe. Unlike matter or radiation, dark energy does not consist of particles and has no known substance or physical manifestation. Its existence explains the observed accelerated expansion of the universe, a phenomenon that has been confirmed by various astronomical observations. Dark energy dominates the universe, constituting approximately 68.3% of its total mass energy content. Dark energy is often associated with a negative pressure that exerts a repulsive gravitational force of the universe, counteracting the attractive force of gravity produced by matter. This repulsive force is believed to be the driving factor behind the universe's expansion, which is not only ongoing, but is also accelerating. The existence of dark energy was first inferred from observations of distant supernovae. In the late 1990s, two independent research teams were studying distant Type 1a supernovae. They expected to find the expansion of the universe was slowing down due to the gravitational attraction of matter. To their surprise, they discovered that the expansion was accelerating. This discovery was a groundbreaking moment in astrophysics and cosmology. It led to the recognition that dark energy must exist to account for this acceleration. The observation of distant supernovae were complemented by other evidence, such as the cosmic microwave background radiation and the large-scale structure of the universe, all of which supported the presence of dark energy. The Friedmann equations, which are key equations in cosmology, can be modified to incorporate the presence of dark energy. These equations describe the expansion of the universe and relate the scale factor, the Hubble parameter, the energy density, and the pressure of the universe. For a universe with dark energy, the Friedmann equation looks like this, where H is the Hubble parameter, G is the gravitational constant, Rho is the total energy density of the universe, K is the curvature parameter, and lambda represents the cosmological constant or dark energy. This equation describes the evolution of the scale factor and the universe as a function of time, and contains various terms that represent the factors influencing the expansion of the universe. Let's break down the components of this equation. H squared is the Hubble parameter squared. H represents the Hubble parameter, which quantifies the rate at which the universe is expanding at a particular point of time. It's often expressed as the first derivative of the scale factor with respect to time. 8 pi g over 3 times rho is the matter term. 8 pi g is a combination of constants where g is the gravitational constant. Rho represents the energy density of matter, both ordinary and dark matter, in the universe. It quantifies the amount of matter present in a given volume. K over a squared is the curvature term. K is a constant that represents the spatial curvature of the universe. The value of K can be positive 1, negative 1, or 0, indicating a closed, open, or flat universe respectively. A is the scale factor, which characterizes the size of the universe at a particular time. It represents how the universe expanded or contracted over time. The term negative k over a squared takes into account the effect of the spatial curvature of the universe's expansion. It can act as a gravitational attractive or repulsive term, depending on the sign of k. Lambda over 3 is the cosmological constant term. Lambda is the cosmological constant, often associated with dark energy. It represents a form of energy associated with empty space itself and exerts a repulsive gravitational effect on the universe. The term lambda over 3 accounts for the influence of dark energy on the expansion of the universe. Another important formula that relates dark energy to the expansion of the universe is the acceleration equation. This specific equation describes the acceleration of the cosmic scale factor, which characterizes the expansion or contraction of the universe as a function of time. A double prime t over at is the acceleration of the scale factor. At represents the scale factor of the universe at a particular time t. It describes the size of the universe relative to its size at some reference time. A double prime t is the second derivative of the scale factor with respect to time, which represents the acceleration of the scale factor. This term describes how the rate of expansion or contraction of the universe is changing over time. Negative 4 pi g over 3 times rho plus 3p is the effect of matter and radiation. G is the gravitational constant. Rho represents the energy density of matter and radiation in the universe. It quantifies the amount of mass energy per unit of volume. P represents the pressure of matter and radiation in the universe. The term accounts for the gravitational effects of matter and radiation, including their contribution to the deceleration or acceleration of the universe's expansion. And lambda over 3 is the cosmological constant, which is the same as the previous equation that I've already explained. This equation relates the acceleration of the cosmological scale factor to the combined effects of matter, radiation, and dark energy. It provides a fundamental description of how the expansion of the universe is influenced by the various components of the cosmic energy budget. This equation is a key element in the Friedmann equations and is used in cosmology to understand the dynamics of the universe's evolution, including its past and future behaviors. Dark energy remains one of the most profound mysteries in astrophysics and cosmology. Despite its mysterious nature and our limited understanding of it, its existence is supported by a wealth of observational evidence. The discovery of dark energy has fundamentally transformed our understanding of the universe, leading to the realization that it is not only expanding, but it is doing so at an accelerated rate. The mathematical formulations used to describe dark energy, particularly through the equation of state parameter and the modified Friedmann equations, play a crucial role in our efforts to unravel the mysteries of the cosmos and the nature of this force that shapes our universe. Now that we have learned the universe is expanding and that dark energy is responsible for this expansion, can we use these facts to determine how the universe will end? Why, yes. Yes, we can. There are 3 ways the universe could end. One that is not likely, one that is likely, and one that is extremely weird and terrifying. First way the universe could end is in a big crunch. The concept of the Big Crunch is a fascinating but uncertain hypothesis in cosmology that suggests the possibility of the universe collapsing in on itself. following the expansion driven by the Big Bang. This concept, once widely entertained, has lost favor among astrophysicists for several compelling reasons. One of the key factors leading astrophysicists away from the Big Crunch hypothesis is the discovery of dark energy. The second is the observations of galaxies' redshift, evidence of the universe's ongoing expansion, as it has been constantly supported by various measurements, including those from the cosmic microwave background radiation. These observations indicate that the universe is not only expanding, but it's also accelerating in its expansion, a trend contrary to the expectations of a Big Crunch. Third, cosmologists use a parameter known as omega to describe the ratio of the actual density of the universe to the critical density required for a flat universe. And no, a flat universe isn't the same as a flat Earth, it is just dealing with angles in space. A flat universe is one in which the expansion rate will gradually slow down, but never reverse into a Big Crunch. Observations suggest that the universe's omega value is very close or equal to 1, indicating a flat or nearly flat universe. Fourth, to achieve a Big Crunch, there would need to be enough matter in the universe to eventually overcome the expansion driven by dark energy. However, current observations suggest that the universe's total matter density is not sufficient enough to halt the expansion to lead to a contraction. And finally, the precise measurements of the cosmic microwave background radiation align with the predictions of a universe that will continue to expand rather than contract into a Big Crunch. The most likely scenario of the end of the universe, based on our current understanding of astrophysics, is the heat death of the universe, also known as the Big Freeze. It is the theoretical prediction of the ultimate fate of the universe, where all physical processes cease and the cosmos becomes a cold, dark, and lifeless expanse. The heat death scenario is a consequence of the second law of thermodynamics, which states that entropy in a closed system tends to increase over time. Entropy represents a measure of randomness in a system. In the context of the universe, this law implies that over cosmic timescales, systems naturally evolve from states of lower entropy into higher entropy. The concept of heat death envisions a future universe in which entropy reaches its maximum possible value, resulting in the complete exhaustion of available energy for any meaningful purposes. In this state, the universe becomes a vast, cold, and lifeless expanse where all physical and chemical processes come to a halt. There are several key aspects of the heat death of the universe. In this scenario, the universe's expanse continues indefinitely. Galaxies move further apart, and the cosmic horizon expands, isolating galaxies from one another. As the universe expands, entropy increases. Matter and energy become more uniformly distributed, and temperature differences between regions diminish. Stars, the primary sources of energy and heat in the universe, eventually exhaust their nuclear fuel and fade away. No new stars form, leading to the gradual dimming of the cosmos. Over an extremely long time frame, the universe cools down as it expands. Eventually, the temperature drops to near absolute zero, rendering the universe frigid and devoid of thermal energy. Even black holes, the last remaining sources of energy in the universe, will eventually lose their mass due to Hawking radiation and eventually evaporate. How long will it take for the universe to experience heat death? A long time. A very, very long time. Well, how long is a long time? According to the book The 5 Ages of the Universe, we are in the second era, the Stelliferous era, which began 300 million years after the Big Bang and will last to 100 trillion years. As younger stars die off and the only remaining stars are red dwarfs, galaxies will begin to change color. Right now, spiral galaxies are blue in nature due to the young, hot stars. Blue stars do not live as long as red stars since they fuse their hydrogen at a rapid rate. As the blue stars start to die off and no new stars form, galaxies will shift from blue to red in color. In a trillion years, the only stars in the universe will be red dwarfs. Due to red dwarf formations in planetary nebulas, red dwarfs could stick around for about 100 trillion years. But these two will die off eventually. Once the last stars die off, the only objects that will produce noticeable energy will be the corpses of stars, white dwarfs, neutron stars, and black holes. This 100 trillion years is 10,000 times the current age of the universe. After the last stars die, we end the Stelliferous era and begin the Degenerate era, which will last from 100 trillion years to 10 to the 40 years. This era is called the Degenerate era because it is degeneracy pressure that is keeping white dwarfs and neutron stars from collapsing in on themselves. Electron degeneracy pressure and neutron degeneracy pressure respectively. The universe will be dark to human eyes, but actually quite bright in the infrared wavelength. Neutron stars and white dwarfs start off extremely hot and cool off over time. In a few trillion years, these stars will have cooled off to room temperature. Due to dark energy, our cosmic horizon is shrinking. Currently, the universe is expanding at 71 kilometers per second per megaparsec. Wait, kilometers, that can't be right. How much is that in freedom units? A parsec is 3.26 light years, so a megaparsec is a million times that, or 3,260,000 light years. So, for every 3 million light years away from us, the universe is traveling 71 kilometers per second away from us. 6 million light years away, the universe is traveling away from us at 142 kilometers per second, and so on. We eventually get to the point where the universe is expanding away from us faster than the speed of light. You might be thinking that nothing can move faster than the speed of light. Nothing can move through space faster than the speed of light, but space can do whatever it wants. In 1 quadrillion years, all planetary orbits will have been disrupted and there will be no planetary systems remaining. Every object would have been flung out into the void of space. In 1 quintillion years, megagalaxies will begin to fall apart due to the countless interactions between black dwarfs, black holes, and other stellar remnants. In 10 quintillion years, everything will have either fallen into the supermassive black hole at galaxy centers or have been flung out into the void of space. After 10 to the 40 years, everything has burnt out and the only things that remain are black holes. Thus, we enter the black hole era. The black hole era lasts from 10 to the 40 to 10 to the 106 years. Most people think of black holes as just sucking things in and it's gone forever. Although technically it doesn't suck, it curves space-time in a way that all future light cones are pointed towards its singularity, but that's neither here nor there. This is not technically true. Black holes actually emit radiation in the form of Hawking radiation. It's actually really cool. There are things that are called virtual particles that are popping in and out of existence all the time. Near a black hole, right next to the event horizon, the point of no return, if a virtual particle pair pops into existence, one particle could fall into the black hole while the other is flung out into space, and that means that the black holes are actually evaporating. This evaporation takes a long time. A black hole with the size of 3 times the size of our sun, the smallest size a black hole can form from a supernova, it will take 10 to the 68 years to evaporate. Even supermassive black holes at the center of galaxies evaporate. They will begin completely evaporating in 10 to the 92 years, and the most massive ones will live until 10 to the 106 years, or a million Google years. As black holes completely evaporate, they will explode, releasing a massive amount of light and energy. During the black hole era, this is the only source of light. After black holes are gone, that's it. There is nothing left. We have encountered the dark era, where time stretches to infinity and it is completely dark, with the universe in perfect equilibrium and maximum entropy. The heat death of the universe stands as a profound and inescapable fate based on the principles of thermodynamics and our current understanding of the universe. This scenario represents the ultimate destiny of our cosmos, where all energy dissipates and the universe enters a state of equilibrium, devoid of any gradients or potential for future changes. The concept of the heat death of the universe presents a bleak and intriguing vision of our cosmos' distant future. While it is based on well-established principles of thermodynamics and our current understanding of our universe's behavior, the exact timeline and details of this scenario remain subject to ongoing scientific investigations and theoretical refinement. The heat death scenario invites contemplation about the vast scales of time and space that characterizes our universe and the challenges of predicting its ultimate destiny. The final way the universe could end, based on our current understanding of physics, is truly weird. The Big Rip is a hypothetical cosmological event in which the fabric of the universe tears itself apart. This scenario is predicated on the idea that dark energy becomes more potent over time. As the universe continues to expand, dark energy's influence becomes increasingly dominant. In the Big Rip scenario, the strength of dark energy grows without bound, leading to several key consequences. In the Big Rip scenario, dark energy's density increases with time, causing the rate of cosmic expansion to accelerate at an ever-increasing pace. As dark energy becomes more potent, it exerts a repulsive force that overcomes gravitational attraction. This force can pull galaxies away from one another, causing galaxy clusters and even galaxies themselves to disintegrate. On smaller scales, the increasing strength of dark energy can disrupt the stability of solar systems. Planets may be torn apart from their parent stars, and ultimately, even the atoms could succumb to the Big Rip. In the most extreme version of the Big Rip, dark energy's influence becomes so overwhelming that not only it tears galaxies, stars, and planets apart, but it fractures the very fabric of space-time itself. Let's look back at our equation for the expansion of the universe. For the Big Rip, what we care about is the ratio of pressure over density. The pressure over density is known as the equation of state and is represented by a W. P over rho equals W. When we add the cosmological constant and solve for the equation of state, we get -1. All this means is when volume increases, density does not go down. So we have a negative for the equation of state and a negative at the beginning of the problem. We get a positive expansion means dark energy is pushing out, increasing the expansion rate. Any expression where the equation of state, density over pressure, is less than -1/3, it will cause an expansion. If W is greater than -1/3, the universe expansion would be decelerating. If -1/3 is greater than W, which is greater than -1, the universe would be expanding, but dark energy would be decreasing over time. If W is less than -1, the acceleration of the expanding universe would be accelerating. The universe is already expanding, and our cosmic event horizon is shrinking. We will be safe from the expansion of dark energy inside our own galaxy due to its gravity, if W stays or is greater than -1. But what happens if W is less than -1? Then even the mass of our combined supergalaxy cannot save us. Once our galaxy is disrupted by dark energy, there is nothing to protect us from the encroaching doom of a cosmic event horizon. The result is that no particles will be close enough to interact with each other ever. If the Big Rip is to happen, it will occur billions of years from now. At 1 billion years before the Big Rip, galaxy clusters would be ripped apart. 60 million years before the end, the Milky Way supergalaxy is shredded. In the last month, the solar system will be pulled apart. 30 minutes before the end, dark energy is strong enough to overcome the gravitational forces of Earth, and it is destroyed. At 10 to the -19 seconds before the Big Rip, all chemical bonds will be disrupted, the forces binding atoms together, then nucleons. The end results would be nothing but individual elementary particles separated by an infinite amount of expanding space. Now this sounds very painful, but will it happen? Not likely. When we look at data from multiple supernovae, the CMB, and other measurements, we get an equation of state extremely close to -1. For example, the Chandra X-ray Observatory has the equation of state at -0.991, and the Planck Observatory has the equation of state as -1.028 plus or minus 0.032. It's not impossible, but it doesn't look like it will ever happen. If it does, it is still 75 billion years away. We have a little bit of time to refine our calculations. Extra bonus part! Remember earlier in the video when I was talking about Hubble's law, where the velocity of a galaxy is moving away from us is equal to Hubble's constant times the distance it is away from us? Want to see something really cool we can do with that equation? So we have V is equal to H naught times D. Now what happens if we divide both sides by velocity and both sides by the Hubble constant? We get this, where 1 over Hubble's constant is equal to distance over velocity. Well, distance over velocity is time, so 1 over H naught is equal to time. Hubble's constant is equal to approximately 71 kilometers per second per megaparsec. 1 megaparsec is equal to 3.0857 times 10 to the 19 kilometers. So that means the Hubble constant is equal to 2.30 times 10 to the -18 over seconds. 1 over Hubble's constant is equal to time, which is equal to 1 over 2.3 times 10 to the -18 inverse seconds, which is equal to time. Whenever you solve this, you get 4.3478 times 10 to the 17 seconds. Now let's do a little bit of conversion. 4.3478 times 10 to the 17 seconds. We multiply that with the fact that 1 minute is equal to 60 seconds, times the fact that 1 hour is equal to 60 minutes, times the fact that 1 day is equal to 24 hours, times the fact that 1 year is equal to 365.25 days. And all of this is equal to time. So whenever we solve this, we get that time is equal to 13.8 billion years, the age of the universe. How cool is that? You use math and the numbers that we learned today to calculate the age of the universe. So there you have it. You learned how and why the universe is expanding, along with different ways the universe could come to an end, and how to calculate the age of the universe. Leave a comment down below on which ending of the universe you like and why. Comments are good for the YouTube algorithm. comments are good for the YouTube algorithm. If you would like to learn more about how we can see objects 46 billion light years away in a universe that is only 13.8 billion years old, click on the video right here. Or if you would like to learn more about Newton's and Einstein's view on gravity, click on the video right here. And always remember, have fun with STEM.